Today we're going to learn Chapter 2, Resistive Circuits. This chapter will be divided into 3 parts. Let's look at Part 1, Ohm's Law and Kirchhoff's laws. A resistor is a passive element. It can be characterized by an algebraic relationship between the voltage across its terminals and the current flow through it. For a linear resistor, the Ohm's law says the voltage Vt that is equal to R times It. So Vt is linearly proportional to the current with the coefficient of R. This constant R is called the resistance of the components. Let's look at this example. It tells us that if R is a fixed value, the larger voltage applied on this resistor, the larger current that you will have. Since we also learned the conductance is the inverse of resistance, Ohm's law can also be written in another form by using the conductance, It that is equal to G times Vt. Since the equation is algebraic, the time dependence is omitted. In this class, we're going to write a V that is equal to R, or I that is equal to G times V. And there are 2 special resistor values. The first one is a short circuit. So in circuit analysis, when we draw a wire, we assume that it has no resistance. Or we can say R is equal to 0, or G that is equal to infinity. Another special case is an open circuit where there's no current flow through this branch. The resistance that is equal to infinity and the conductance is equal to 0. And we also need to know that Ohm's law is just an approximation. It's only valid within a linear range. So in this picture, the red line is describes the actual VI relationship of a resistor. And Ohm's law applies to this linear range. So from the expression of Ohm's law, we know that it has 3 variables, V, R, and I. Or you can say I, G, V. So given 2 of these 3, we'll be able to find the third. So we have a 3 type of problem here. The first case, given the current and resistance, you will be able to find the voltage. So voltage is equal to R times I. Second case, given the current and the voltage, we'll be able to find the resistance. R is equal to V over I. The third case is given the voltage and the resistance, we'll be able to find the current. I is equal to V over R. So remember, we are going to continue using passive sign convention to determine the polarity of voltage and the direction of current. The next topic is about power absorption by resistors. So resistors are passive elements. We know that if we use passive sign convention, we will always get positive numbers in calculate for the power. Resistors absorbs energy. From the previous lecture, we know that P that is equal to V times I. In combination with the Ohm's law, V that is equal to Ri, we can find the power calculation for resistors. If we replace the current I by using V over R, we will have a V squared over R. If we replace voltage V by using I times R, we will have another expression, I squared times R. So these 2 expressions will be very common equations for us to calculate the power absorbed by a resistor. So now in these relationships, we have 4 variables in total, P, V, I, and R. So since we have 2 equations, we know that only 2 of them are independent. So given any of the 2, we'll be able to find the other 2. So I have listed these 4 different cases over here. So given the power and the current, you will be able to find the voltage and the resistance. Given the current, resistance, you will be able to find a V and a P. Give you V and R, you can find an I and a P. Give you P and R, you'll be able to find an I and a V. So you're not required to memorize all these equations. You just need to master these 2 basic equations, how to calculate power and Ohm's law. Then you can derive these equations fairly easily. So next topic, Kirchhoff current law. So in this class, we are going to abbreviate it as KCL. The KCL is based on the consideration of a charge principle. It says charge cannot be created or destroyed. To understand this, we need to define node. So a node is a joint where two or more elements are joined. For example, in this circuit, 1 is a node. So this is our node 1. It's connected between the current source, resistor R1, and resistor R2. So this is a joint. This is also called a node. And similarly, we have node 2 here, node 3 connected to these 4 different branches, node 4 connected to 3 branches, and this is our node 5. A node can only connect several components, but it cannot hold any charge. Think of it as a valve in a pipe system, and this valve cannot hold water. It's basically direct water flows. So the water coming into the valve will be equal to the water flow through the valve. Another concept that we want to learn is a loop that will help us to define KVL, Kirchhoff voltage law. Loop is a closed path that never goes twice over a node. For example, this loop. So if we follow this loop, we'll go through this voltage source first, then through this resistor R, and further this resistor R3. So it completes this loop. This is a closed path, and it doesn't go through any element twice. So this is called a loop. Here's another example. This will be another loop. So this is a closed path. Started from here, and then come back here. And it only goes through the element once. It goes through R5, R2, then further this is I1, the current source, then resistor R3, then voltage source V2, then come back. This is a closed path, and it's called a loop. So this example, is it a loop? This is a closed path, no problem. So let's look at whether it goes through any element twice or not. So it goes through this current source, then this resistor R1 come to this point, then come back, go through the R1 twice. So this is not a loop because it goes through one resistor twice. Another concept is called a branch. So the branch is a component connected between two nodes. For example, this is a branch between node 1 and 3. This is a branch that has one component R1. Between node 1 and 4, there is one branch. And between 2 and 3, there is one branch. Between 3 and 5, and there is another branch with a voltage source. Let's look at Kirchhoff current law. It says the summation of currents flow into a node is equal to sum of the current flowing out of a node. We can also write it in a way as algebraic summation of a current flow into a node is equal to 0. Of course, you can also say algebraic summation of a current leaving a node is equal to 0. So let's look at how we're going to write the KCL equation. By looking at this node, there are 5 different currents connected to this node. If we follow the first expression to write a KCL equation, we have the current goes into the node I1 plus the current goes into the node I5 is equal to the current leaving the node I2 plus I3 plus I4. If we write it by using the second expression, it becomes I1 flow into the node minus I2 leaving the node minus I3 because it's leaving the node minus I4 plus I5 that is equal to 0. Kirchhoff voltage law, or KVL. KVL is derived based on a conservation of energy principle. It says that energy cannot be created or destroyed. From the definition, we know that a voltage is defined as the energy needed to move one column of charge. Assume that we have a charge Q, and we move charge Q from node A to node B. Node A have a node voltage of VA, node B have a voltage of VB. And the energy increase from A to B, that is equal to Q times the voltage potential difference, VB minus VA. If we move the charge, if we have a series of moves of this charge, say from node A to B, then to C, then come back to A, and we know that from the whole process, the energy for this charge stays the same. If we break it down into these three moves, the energy change will be Q times VAB plus Q times VBC plus Q times VCA. And we know that is equal to 0. So since Q is not equal to 0, we can find that VAB plus VBC plus VCA is equal to 0. If we move the charge from the higher voltage end to a lower voltage end, it loses energy. Delta W is equal to Q times VAB. If we move the charge from the lower voltage to a higher voltage node, it gains energy. Delta W is equal to Q times VCD. KVL can be described as the algebraic summation of the voltage drops around any loop must be equal to 0. Let's look at this example. If we want to write a KVL equation for this single loop circuit, started from here, it will be the voltage drop from this resistor VR1 plus the voltage drop on this resistor VR2 plus the voltage drop on this resistor VR3 plus the voltage drop on this current source. Since it's increase, it will be negative Vs. So it will be written like this: negative Vs plus VR1 plus VR2 plus VR3 is equal to 0. And we can do the same thing for this single loop circuit. If we follow this direction, we can write KVL as VR1 minus 5 plus VR2 minus 15 plus VR3 minus 30, that is equal to 0. And the loop doesn't have to be physically connected loop. So let's look at this example. In this example, if we are trying to find a VBE, we can define the loop like this, following this orange line. So if we write the KVL equation, it becomes negative 30 because it's a voltage increase, plus a voltage drop VR1 plus VBE plus VR3, that is equal to 0. So if VR1 and VR3 that is given, we'll be able to find VBE. Of course, you can also define the loop on the other side to find a VBE.